Okay, so welcome to Math 355 Abstract Algebra. So this is lecture 17. We're going to finish up talking about approximating irrationals by rationals. So in the last lecture, we talked about some of the consequences as to why might we care about something like this. Today, we're going to actually see how do you do this and how well can you actually do this. So this leads to the question of trying to find a good metric. How do you want to compare things? What do you want to use? For those of you who have some physics knowledge, for a while, the definition of meter was the length of a certain bar in Paris. This is not a convenient definition. A meter is now defined by, I believe, how much light travels in a certain amount of time, and time is now the fundamental unit, I think, defined through vibrations of like a cesium atom, for how long a transition takes or something like that. So you want to try to figure out what is a good metric for studying something. If I wanted to approximate pi with rational numbers, can somebody give me a way that I might be able to get good approximations for pi? Give me an approximation for pi. It can be really simple.
7/22.
No. Really simple. Much simpler than 7/22. 3. Give me another approximation that's a little bit better.
3/14.
No, 3/14. 1/10.
Oh, well, yeah.
Right. Yeah, sometimes you have to be non-clever. And we can just put things like this. So if I use powers of 10 as my denominator and just truncate the decimal expansion, these will give me a good number of digits. The problem is the number of digits it takes to get a good approximation is quite large. And for a computer, the larger the number you work with, the harder it is for the computer to work with. So we want to try to find good approximations. So you mentioned earlier, pi equals approximately 22/7. That's a much better approximation, and it's using a very small denominator. So the question becomes, depending on the size of the denominator I use, how small can I get? So when I look at pi, and I want to subtract, say, p/q with a rational number, I want to look at it as 1/q to some power. What power can I do? Can I do 1/q, 1/q to the 3/2, 1/q squared, 1/q cubed? How close can I get? And I want to do this infinitely often. I don't want to get just once. And maybe to give myself a little bit of freedom, maybe I'll put some constant here that's independent of p and q. I only care about how well I'm doing relative to the denominator. If I'm off by a multiplicative factor of 5 or 7, I don't really care. But I want to see how well can I approximate. And a good metric is going to be the size. The smaller the denominator for a given level of approximation, the better job I'm doing. So the first result is infinitely often we can approximate an irrational number alpha by a rational number and be off by at most 1/q. Can you replace the less than or equal to with a less than? If alpha minus p/q equals plus or minus 1/q, what does that tell you about alpha? It's rational. So then alpha would just be p/q plus or minus 1/q is a rational number. And so I now just shift the pen to white, and I just cross off equality there. And we've already improved the theorem, right? There are some cases where this actually makes a difference, most of them don't. So here's the proof. Without loss of generality, we might as well assume alpha is in the interval 0, 1. Because if it's not, I can just subtract an integer and move it down there. And so now, here's the interval 0/q, 1/q, 2/q, 3/q, I won't say the next one, p/q, p plus 1/q, ... all the way down to q/q. And I claim that there has to be some p such that alpha lands in one of these intervals. Because I'm moving by steps of 1/q. Alpha has to live in one of these intervals. So without loss of generality, it's in this interval. So let's let IP be the interval, P over Q, P plus 1 over Q. I don't have to include the endpoints because I know alpha can't be an endpoint. Thus, alpha minus P over Q has to be at most 1 over little q, because it's in an interval of length 1 over q. So I can approximate my number within 1 over q just by taking steps. I can't jump by so much that I get too far away. This is not an impressive result. This is essentially what we just did when we started off by looking at approximations to pi. I just took larger and larger powers of 10, and so I'm off by 1 over that power of 10. Not a big deal, just truncating my decimal. So to do better, I need to introduce some mathematics. And so what we're going to do is we're going to do the pigeonhole principle or the box principle. So hopefully you've seen this before in some class. If not, I'm happy to be the one to introduce you to it. It basically says, imagine we have n+1 pigeons and a very nice pigeon gun which gently guides the pigeons without hurting them into n boxes. Then at least one box has to have at least 2 pigeons. Imagine we have boxes, box 1, box 2, ... box n-1, and box n. And then we have a bunch of pigeons, pigeon 1, pigeon 2, pigeon 3, ... pigeon n-1, pigeon n plus 1. And we somehow start assigning the pigeons to boxes. The claim is that at least one box has to have at least 2 pigeons. And the proof is not so bad. If each box has at most 1 pigeon, accounts for at most n times 1, which is less than n plus 1. We have n plus 1 pigeons that only accounts for n. Another proof is the average number of pigeons per box is n plus 1 over n, which is greater than 1, and it is an integer. So it's at least 2. So no integer smaller than 1, I'm sorry, greater than 1 before 2. So you have to have at least 2 pigeons in one box. It's amazing how powerful Dirichlet's pigeonhole principle is. In order to use it, you have to identify 2 things. What do you have to identify? Not the number, although that's part of it. You have to identify what the pigeons are and what are the cages. Cages is a no-no word, as my niece would say, that has negative connotations. So we will say boxes, palaces, spas, whatever nice place we're sending the pigeons to. Kitchen would not be an appropriate word. All right, here's one of my favorite pigeonhole problems. And if you want more and stuff like this, here is a lecture from when I was teaching the little questions, which is basically mathematics of problem solving. So imagine I give you n integers, a1, a2, all the way up to an. The claim is that there is a subset that has a sum that's divisible by n. And of course, the question is, okay, so I'm saying if I take n elements, any n positive integers, I'm going to have something like this. What if I only have n minus 1? You trying to get into the class? Yep. Okay. Yep. And so in a situation like this, what if we only had n minus 1? So can anybody give me a possible choices of the values of a1 through an where all sums are not going to be divisible by n if I only have n minus 1 items? So without loss of generality, if I want to find a sum that's divisible by 12, where can I assume all the numbers live without loss of generality? 0 to 11. If any of the numbers are 0, then clearly I'm going to have a sum that's divisible by n. Just take whichever one of those numbers is 0. So I can assume that all of my numbers are between 1 and 11. Can you give me a subset of 11 numbers so that no sum is divisible by 12? Is there such a sum? So can you give me 11 numbers? Each of them is between 1 and 11, such that no sum of theirs is going to be a multiple of 12. So if have n minus 1 items, try a1 equals a2 equals an minus 1 equals 1. That won't work. So this tells us that if we had fewer than n items, we might have problems. Now, how many non-empty subsets of n elements are there? If you n elements, how many non-empty subsets can I have? Two to the n minus 1. I have 2 choices for the first element, 2 for the second, all the way up to 2 for the last, and then I have to subtract 1 because I have to throw away the case when I chose nothing. And that's going to just be 2 to the n minus 1. So when you look at how many subsets we have a tremendous number of subsets. I have, the number of subsets I have is exponentially growing in n. I just have to find one subset. Okay. Without loss of generality, each AI is in 1, 2, ... n minus 1, as if an AI equals 0 or a multiple of n, we're done. So now we have to figure out what are the pigeons, what are the boxes. Any thoughts on what we should do for the boxes? So we're trying to show that we have a sum of elements that adds up to a multiple of n. None of the a's are multiples of n, because otherwise it's trivial. What can we assume? What should our boxes be? So this is the hard part. We're looking at multiples of n, right? So how do you tell if a number is a multiple of n? You divide by n and you look at the remainder. So what do you think the boxes should be? The remainders. So our boxes are the remainders mod n. So we have 1, 2, 3, ... n minus 1. The pigeons, that's the hard part. We have 2 to the n minus 1 possible subsets. I need to just choose a subset with n elements because I have n minus 1 boxes. I need n pigeons. So a really good choice of subsets is let's let S1 be A1. Let's let S2 be A1 plus A2. Let's let S3 be A1 plus A2 plus A3, all the way down to Sn is A1 plus An. These are very special sums. I'm just adding one more term as I march down. I have n pigeons. I have n minus 1 boxes. What do we know? So what must be true? Good. So without loss of generality, S, J, and SK in same box, let's say k is greater than j. So sk minus sj is going to be a j plus 1 plus a j plus 2 plus dot 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 plus ak is a multiple of n, as sk minus sj has remained a 0. And so this problem was, a bit tricky in terms of trying to figure out what should we choose for the boxes, what should we choose for the pigeons. We know that we don't have to worry about remainder of 0, because if we have a remainder of 0, we're done. So we can assume that we're in a situation where we don't have any remainders of zeros. Okay, any questions about this? So this is one of my favorite pigeonhole problems because it's not immediately clear what the pigeons and boxes should be. And there's so many possible subsets. The fact that this is the nice one to do. I need just n elements out of 2 to the n. That's like a logarithmic scale. There's so many possibilities. Okay. So now, infinitely often, if alpha is irrational, we can find rational numbers p over q such that it's at most 1 over q squared. Can somebody give me a stronger theorem than this? Not significantly stronger, but a little bit stronger. So I claim infinitely often you can find a rational such that the difference alpha minus p over q in absolute value is less than or equal to 1 over q squared. How could you make this a little bit stronger? It's the same as we did earlier. Get rid of the equality, right? If alpha minus p over q equals plus or minus 1 over q, then that implies alpha equals p over q plus or minus 1 over q is rational. So we can improve it a little bit without too much work. So what result do you think might be useful for proving this? What idea might be useful for proving this? Yeah, based on the fact that we've just done the pigeonhole principle, we've just introduced it, we've just done an example, and we haven't used it for the lecture today, it's not unreasonable to suspect that maybe the pigeonhole principle is going to be useful for this. Well, if we're going to use the pigeonhole principle, we have to identify boxes and pigeons. So let's choose a big Q and look at alpha 2 alpha dot 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 q plus 1 alpha mod 1. And so again, here's 0 over q, 1 over big Q dot 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 q over q. So I have a bunch of intervals of length 1 over q. And I look at these numbers mod 1, and I have big Q plus 1 of them. So what must be true if I have big Q plus 1 numbers and I have Q intervals? So what must be true? So 2 of them have to be in the same interval. So there exist, integers, a1, a2, n1, n2, such that a1 alpha minus n1, that's going to be the multiple of alpha, and then we're going to subtract off its integer part, so it's now in 0, 1. Minus a2 alpha minus n2, the fractional part of the second multiple. This distance has to be less than 1 over big Q. It's strictly less than, because if it was actually equal to, you would then get that alpha had to be rational. All right, so this is the same as a1 minus a2 alpha minus n1 minus n2 is less than 1 over big Q. And here, 1 is less than or equal to a1, a2, less than or equal to q plus 1. Because these are my multiples. I can divide through by a1 minus a2 because a1 minus a2 is not 0. They're distinct. What's the smallest a1 minus a2 could be? So because they're distinct integers, what's the smallest a1 minus a2 could be? Or we'll do it in absolute value if you want. What's the smallest a1 minus a2 could be in absolute value? It has to be 1. They're distinct numbers, so the difference has to be at least 1. What's the largest it could be? Well, the largest is if one of them was q plus 1 and the other one was 1. So the largest it can be is big Q. So now if I divide through by a1 minus a2, which I can because it's not 0, I get alpha minus n1 minus n2 over a1 minus a2 is less than 1 over a1 minus a2 times big Q. So I want to try to find a rational to approximate alpha. What should I take for my numerator? What should I take for my denominator? So when you look at this, what's a natural candidate for that rational approximation? Yeah, so let's take P to be n1 minus n2, Q to be a1 minus a2. And if I want to, without loss of generality, I can assume a1 is greater than a2. Let's just choose them in that order. So now I get alpha minus P over Q is less than 1 over little q big Q. But which is larger, big Q or little q? Well, we know little q is at most big Q. So if I replace big Q with little q, I can't make this smaller. It might stay the same if big Q is the same as little q, but it definitely can't get smaller. It might get a little bit larger. This is going to be less than or equal to 1 over little q squared. So we just found a choice of P and Q such that alpha minus P over Q is at most 1 over little q squared. We unfortunately have to do this infinitely many times. We've done it once. Well, let's just do it again with a bigger Q. Do again for a sequence of big Q going to infinity. The problem is, what if we keep getting the same P over Q every single time? This just generates a P over Q. Maybe it keeps generating the same P over Q every single time. This is how careful you have to be when you're doing proofs like this. Well, if you think about what's going on, if I keep generating the same P over Q, here's alpha right over here. And let's say here's my P over Q. This is going to be a fixed distance away. Choose Q so big that 1 over big Q is now less than alpha minus P over Q. This is telling me I can't keep getting the same P over Q every single time because this distance is less than 1 over big Q. If I drop the 1 over little q, I've just got a bigger result. So I can't get the same P over Q infinitely often. As alpha minus P over Q is less than 1 over big Q, cannot keep getting same Q. Keep getting same P over Q. So do get infinitely many. So I'll leave it to you to just make this rigorous, but the whole point is we keep changing different things. In one of the times we replace the big Q with a little q, and the other we drop the little q. And that's enough to show that we can't keep getting the same thing. We can choose big Q so large that it has to be a different rational that's coming into play. Okay. It's always interesting to ask, what's the best you can do? If you're willing to do a little bit more work, which I'm not for a class like this, but if you are, you can actually show that you can get within 1 over q squared root 5 infinitely often for any irrational number. Interestingly, if you look at the golden mean, 1 plus root 5 over 2, coming from the Fibonacci numbers, you can't do better than 1 over q squared root 5. In this sense, the golden mean is the most irrational of all irrational numbers. There is no number that is harder to approximate by rationals than the golden mean. Have you seen continued fractions? If you've seen continued fractions, the golden mean's continued fraction is all ones. Whenever you have a digit that's greater than 1, it gives you a better approximation when you truncate it. And so because the golden mean is all ones as small as possible, that's why it's so bad. So again, a lot of wonderful stuff going on here, but you can't do better than 1 over q squared root 5 infinitely often for all numbers. For some numbers, you can absolutely do better. But if you want a result that holds all the time, this is the best you can do. Okay. Now, the following theorem earned Roth a Fields Medal. So let's let alpha be a real algebraic number, so it's a root of a polynomial with integer coefficients. You might want to say, well, should I be using rational coefficients? Well, if I have a root is where f of alpha equals 0. If my coefficients are rational numbers, let's just clear the denominators. So I might as well assume that my polynomial has integer coefficients. What Roth proved was that no matter what algebraic number you take, you can't do better than 1 over q to the 2 plus epsilon infinitely often for any epsilon. So I can't do better than 1 over q cubed infinitely often. I can't do better than 1 over q to the 2.1 infinitely often. But we know we can do 1 over q squared. This is a way to prove certain numbers are transcendental. If I can show I can approximate this number as well as 1 over q cubed infinitely often, by Roth, it can't be algebraic. Unfortunately, if I want to use this to prove a number is transcendental, I have to prove Roth's theorem. Roth's theorem is involved to prove. If you are patient, you can go through the analysis. It's not horrible, now that somebody has, been the trailblazer, and you can follow it line by line, but it's an involved proof. We are not going to do that in an hour. This slide I'm just putting here for completeness. If you want to talk a little bit about a sense of how much of the interval 0, 1 is actually taken up by numbers that can be approximated to a given degree. So if you've done some real analysis, you can look at something like this about how much we have. The next slide, which again, I'm not going to really cover, is applications of Roth's theorem. You can use it to bound how many solutions you can have to certain equations, like x cubed minus 2y cubed equals an integer a. You can show that there's only finitely many solutions to something like that by Roth's theorem. We're not going to prove Roth's theorem. We're going to prove Liouville's theorem. And this is why after Liouville's theorem, we'll talk about Liouville numbers. So what Liouville is able to show is that if alpha is a real algebraic number of degree d, then alpha is approximated by rationals to order at most d. So Roth says no matter what d you have, you can only do d equals 2. You can't approximate more than 1 over q squared. What Liouville said is that's a little bit too hard to prove, so I'm going to allow my exponent to grow with the degree of the polynomial. Roth says it doesn't have to grow with the degree of the polynomial, but Liouville said I can prove that it is at most d, and that's going to be good enough for some applications. What's the simplest d you think we should try? 1. Always start easy. Let's try d equals 1 and see what we can get. Take d equals 1. Let's say we have alpha is algebraic of degree 1. So there exists a polynomial f of x equals ax plus b with a not equal to 0 and f of alpha equals 0. So what can you tell me about alpha if f of alpha equals 0? It's a root. So what can you tell me? Be more specific. It's a real algebra, but be more specific. You now know a alpha plus b equals 0. Therefore, what can you tell me about alpha? It's minus b over a, which is a rational number. So the real algebraic numbers of degree 1, they're just rational numbers. Let's say we're trying to approximate alpha by p over q. So let's assume p and q are relatively prime. And let's look and see how close can p over q be to alpha. So that would be minus b over a minus p over q. That's going to be minus bq minus ap over aq. What can you tell me about the numerator? So what must be true about the numerator? Yes, the one on top.
Okay. It wasn't. Oh, wait.
Well, we're doing absolute values. So if you're saying, well, what kind of number is the numerator? Well, you can be more, the numerator is rational, but you can do better than rational. It's an integer. You know, a, b, p, and q are integers. So I have an integer over an integer. What kind of integer is the numerator? Can you give me any information about what the integer is or is not? So what's the first integer we should investigate as a possibility for the numerator? 0. What would it mean if it was 0? Then it would mean alpha equals p over q. And we're trying to choose relatively prime p over q to equal this minus b over a. Can we have two different relatively prime rationals being the same number? No. So we know the numerator is not 0. So the numerator is not 0. That alpha minus p over q is greater than or equal to 1 over a q, or I'll put the 1 over a outside, times 1 over little q. So what this is saying is I can't approximate a rational degree 1 by rationals better than some multiple of 1 over q, 1 over its denominator. I can't get too close. Now, if I give you 17 over 35, I'm not going to be able to get much better than 1 over 35 away. So we had this 1 over q squared before for irrational numbers. We can't get rationals extremely close. This is kind of sad, right? We can't find a good rational approximation to alpha. Do we care that we can't find a good rational approximation to alpha? Why not? Alpha's rational. There's no need to try to find a rational approximation to alpha if alpha is already rational. There's actually a really good rational approximation with an error of 0. Right? Don't try to find a rational with a larger denominator that does better than alpha. You're not going to. So, okay, this result is a little bit negative, but when you think about it, it's not a big deal. Right. So the next thing I want to talk a little bit about is separability, or how to tell if f of x has repeated roots. So f is going to be a field, big F is a field, and this is chapter 8, which we'll get to on Tuesday. So for us, typically the field is going to be the rational numbers. Maybe it'll be the real numbers. And we take, maybe the complex numbers, and we take a polynomial, non-zero, then there's a theorem that says that there is some extension field in which it factors completely, so that we can write it as a product of x minus alpha 1, x minus alpha 2, and so on. The polynomial is said to be separable if the roots are distinct. And the big result is if you have a field and you have a non-constant polynomial, then f is separable if and only if the greatest common divisor of the polynomials f of x and f prime of x equal 1. Now, when you think about this, if you're me, you're happy because now we're doing analysis and not algebra. I love analysis. I love derivatives. But for derivatives, you need a kind of continuous spectrum to work with. You want the limit as h goes to 0. We don't have that in an arbitrary field. So what we say is, what if we just ignore that? We only need derivatives for polynomials. And let's create what we'll call the formal derivative. Anybody want to give me a proposal for what the formal derivative of x to the n should be? Yeah, let's define the formal derivative of x to the n to be nx to the n minus 1. When we work over the reals, this comes by calculus and limits. Let's just define it formally like this. You can then show the sum rule holds, the product rule holds, the chain rule holds. You can show everything holds if you make this as your definition of the formal derivative. And it turns out that f is separable if and only if the GCD of f and f prime is 1. It's actually pretty easy to determine the GCD. Just like we said, if I want to calculate 357 divided by 11, we have the division algorithm. We saw something like this when we did the Euclidean algorithm. It turns out you can extend that in a case like this when you have an integral ring. And so we can very easily calculate the GCD. If I wanted to look at a function directly, that could be very painful. If I give you, let's say f of x is some constant x minus alpha squared times g of x, then g prime of x, if we do a little bit of work, is going to be c times 2 x minus alpha g of x plus c x minus alpha squared g prime of x. Alpha equals 0 if alpha is a repeated root. So if we have a repeated root, when we go through and we do this calculation, we'll see that it's going to be, there'll be some polynomial x minus alpha that divides both f and f prime. And so there's a really nice, simple test to find something like this. The other thing we're going to be assuming is we will want f to be minimal for alpha. So f of alpha equals 0, and f is irreducible. Can somebody give me the roots of x squared minus 1? I'm sorry? I'm sorry, I said the wrong thing. I said x squared minus 1, but I wrote x squared minus 2. What are the roots of x squared minus 2? Plus or minus root 2. If I give you the polynomial x squared minus 2 squared, the roots are still going to be plus and minus root 2, but this would be stupid to look at this polynomial to try to understand the square root of 2. This is not the smallest degree polynomial that has plus and minus root 2 or plus root 2 or minus root 2 as a root. So rather than studying this, which is clearly not reducible, I would just study x squared minus 2. The other thing is we will assume f has no rational roots. If did, we can write f of x as ax minus b times g of x. And so whenever I'm trying to find a polynomial f that this algebraic number alpha satisfies, I can pull out all the rational roots and just get rid of them. And alpha is going to be an irrational number, so it's not going to set ax minus b equal to 0. Okay. You need a couple of that are technically called no-shift theorems from calculus. These are the truly obvious once you listen to them. The first is the intermediate value theorem. Imagine you start 5 miles from home and you end 12 miles from home. At some point of time, if your distance is a continuous function, will you 7 miles from home? Yes. We have no transporters. You can't get from 5 miles away to 12 miles away without getting 7 miles away. What about 3 miles away? If you start 5 miles from home, you end 12 miles from home, at some point in time, must you have been 3 miles from home? Yes or no? We started 5 miles from home. We end 12 miles from home. At some point, must we be 3 miles from home? No, we might be. My son's car was being worked on yesterday. I left the dealership. And so at some point in time, I am 2 miles from the dealer. I was 5 miles from the dealership. And I realized, oh crap, I forgot something in the car. And I'm in a loaner. Do I go back and get it? Yes, I actually need it. And so I start driving back. And I'm now 3 miles from the dealer. Screw it. It's not worth the pain of going back. They need me at Lanesborough Elementary to do math. But the fourth graders, I'm not going to go back to the dealer. I will go to Lanesborough Elementary. And I go there. That's a perfectly valid situation where I started off at 5, I ended 12, but at some point in time, I was 3 miles away. Another possibility is I start off at 5, realized I forgot something, said, screw it, I'll just get it later. I can deal with not having it for a couple of hours. So you're not guaranteed that you will have it at some point. You might, but you might not. The next one is if in addition to the function being continuous, if it's often differentiable, more is true. So if f is differentiable, then there is some c in the interval such that f of b minus f of a is f prime of c over b minus a. You can rewrite this as f prime of c is f of b minus f of a over b minus a. And you can interpret this as, f of b minus f of a, that's the distance traveled. B minus a is the time elapsed. So at some point in time, you're traveling the average speed. This is another no-brainer. Of course, this must be true. And so I'm going to do the rigorous mathematical writing. I am going to just do the proof by informal conversation. Okay? So here's the proof by informal conversation. Proof. If speed is constant, is there ever a time when you're traveling at the average speed?
Yes.
Yes. What time? I'm sorry? The whole time. If speed is constant, always at average speed. So if speed is not constant, could you always be traveling below the average speed? No, if my average speed is 50 and I'm always traveling below 50, I'm not going to be averaging 50. Could I always be traveling above the average speed? No, similar argument. So if the speed isn't constant, at some time, average speed is less than instantaneous speed. And at another time, the average speed is greater than the instantaneous speed. So now what do we use? So at some point in time, you're traveling slower than the average speed. At another point in time, you're traveling faster than the average speed. We're assuming the function is differentiable and that the derivative is continuous. What must be true? And what theorem is that by? I'm sorry? So what theorem tells us if we're below the average speed at some point and above the average speed at another, at some point we must have gone through the average speed because the speed is continuous. Intermediate value theorem, which is probably why we did the intermediate value theorem before doing the mean value theorem. So done by intermediate value theorem applied to speed. So these are two really intuitive results from calculus. The mean value theorem is actually very useful it allows us to say, f of x minus f of a over x minus a is f prime of c for some c, which means f of x is f of a plus f prime of c times x minus a. It's like a Taylor series. We don't know where that point C is, which is a little bit annoying, but the mean value theorem is essentially giving us some kind of approximation. You should compare this to the tangent line. It's dangerous, recalling these concepts, but the tangent line is y would be f of a plus f prime of a x minus a. And so if this is my function, and here's my point A, then this would be the tangent line. It would be going through the point A comma f of a with slope f prime of a. So the mean value theorem is actually pretty close to the tangent line. It's just we don't know what point we should be evaluating things at. Okay, so now we are ready for Liouville's theorem. Let alpha be a real algebraic number of degree d, then it's approximated by rationals to order at most d. I can't do 1 over q to the d plus epsilon infinitely often. I can't do 1 over q to the d plus 1 or 1 over q to the d plus 2. I can't do anything like that. I can't do better than 1 over q to the d infinitely often. I can have maybe a constant in front of it. I could have 2, 1/2. I don't care about that. But the power of the denominator, I can't do better than d. So without loss of generality, f has no rational roots, and alpha is not a repeated root. So what that means is f prime of alpha does not equal 0. Okay, so f of alpha equals 0, f of x equals a sub d x to the d plus dot 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 plus a1x plus a0. So alpha is going to be a root. This polynomial doesn't have any rational roots. Alpha is a root of degree 1. So if I want to look at f of alpha minus f of p over q, this is just the same as the absolute value of f of p over q. So that's going to be a d p over q to the d plus dot 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 plus a1 p over q plus a0. So I have a bunch of fractions. How do you add fractions with different denominators? So how do we add fractions with different denominators?
Just multiplying those parts by the difference in denominator. Yes. Common denominator.
Common denominators, right? So this is trying to recall things that you may not have seen for many years. We need to find common denominators. Every now and then, not by choice, I turn out to be a nice person, right? It occasionally happens. What are the denominators? 1, q, q squared, q cubed, q to the 4th, all the way up to q to the d. It's not that hard to figure out what the common denominator is. What's the common denominator? Q to the d. Now, actually, I'm really not a nice person because the denominators, maybe there is some cancellation because I do have these numbers a sub d. I know p is relatively prime to q, but maybe a sub d is a multiple of q.
Maybe not.
But we know that at the very least, q to the d works. So we can do q to the d. It is possible that the greatest common denominator is a little bit less than that if we do some cancellations, but we don't need to. We know that this is equal to a to the d, p to the d, plus a sub d minus 1, p to the d minus 1 q, plus dot dot dot, plus a1 p q to the d minus 1 plus a0 q to the d, all divided by q to the d. What kind of number is the numerator? It's an integer. And what kind of number is the denominator? Integer over integer. Wonderful. Can you be more specific about the integer that's in the numerator? It's not 0. Why is it not 0? So what would happen if the numerator was 0? Then p over q would be a root. Then f of p over q equals 0, and we're assuming that f has no rational roots. So we've already removed the rational roots, so we know that the numerator is not 0. So what do we know about the absolute value of the numerator? So it's an integer, it's not 0. What must be true about its absolute value? It's greater than 0. We know that this is going to be greater than or equal to 1 over q to the d. So this is the second time we've used the fact that the absolute value of a non-zero integer is at least 1. This now bumps this up to a technique. A technique is something you use multiple times. This is extremely powerful for a lot of arguments like this. So we have 1 over q to the d is less than or equal to f of alpha minus f of p over q in absolute value. So let's just rewrite it where we have some more space. 1 over q to the d is less than or equal to f of alpha minus f of p over q. Can you think of anything we could use to try to evaluate f of alpha minus f of p over q? What could we use to try to study that? Any thoughts? Yes. Yeah. Well, we know the numerator is an integer. We know the numerator has to be at least 1 in absolute value. So if I just replace the numerator in absolute value with 1, so that's why it's going to be greater than or equal to that. So we know 1 over q to the d is less than or equal to f of alpha minus f of p over q in absolute value. What could I use? What theorem to try to understand f of alpha minus f of p over q? The mean value theorem. There's probably a reason, if you look at the notes, why we just did the mean value theorem just a few moments ago, right before getting into here, right? It was to have the mean value theorem at our disposal. Whenever you see something like f of a minus f of b, f of x minus f of y, think mean value theorem. So this tells us that this is going to be equal to the absolute value of f prime of c times, oh, this is good, alpha minus p over q. And we're trying to understand how close can p over q be to alpha. All of a sudden, we now have something involving p over q. So as alpha is not a repeated root, f prime of c does not equal 0. I'm sorry, if c is close to alpha. So if I'm trying to find a good rational approximation to alpha, I'm not going to be a moron. If I'm trying to find a good approximation to pi, I'm not going to look for p over q that is around 100. I'm going to look for p over q that's around 3.14, something like that. So I can assume that, c is very, very close to alpha. So f prime of c, I can bound it from above and below. So there exists, let's say, big C1, big C2, such that 0 is strictly less than big C1, less than or equal to f prime of c, less than or equal to big C2, if c is close to alpha. So I know I don't have 0. Now, another way I know I can't have 0 is if f prime of c equals 0, then I would have 1 over q to the d is strictly less than is less than or equal to 0. Well, no. Right? I can't have a positive number like 1 over q to the d being less than 0. That would be a contradiction. So I know f prime of c can't be 0. I just want to make sure I'm not dividing by 0. I'm not doing anything illegal. So I get alpha minus p over q is going to be greater than or equal to 1 over, all right, so the largest f prime of c could be would be c2 would be like 1 over c2, 1 over q to the d. Okay. So what this is telling me is if I give you a rational approximation to alpha that's pretty close, I can't be closer than a multiple of 1 over q to the d. And that's a fixed multiple. And so as my denominator gets larger and larger and larger, I can't be that close. So imagine we have infinitely many, relatively prime p over q such that alpha minus p over q is less than or equal to 1 over q to the d plus epsilon. Well, that's 1 over q to the epsilon, 1 over q to the d. Eventually, what can you say about 1 over q to the epsilon and 1 over c2? As q gets really, really large, which is going to be smaller, 1 over q to the epsilon or 1 over c2? One over q to the epsilon is going to be smaller. So once q is large, we would get alpha minus p over q is less than or equal to 1 over q to the epsilon, 1 over q to the d, which is strictly less than 1 over c2, 1 over q to the d, which is less than or equal to alpha minus p over q. Impossible. You cannot be strictly less than yourself. So this proves that I cannot approximate alpha infinitely often better than 1 over q to the d. I can't do 1 over q to the d plus epsilon. What Roth showed is that you don't have to let the power of q grow with the degree of the algebraic number. He said it's enough to always do 1 over q squared. That is way more work than we can do. If you truly care, I can give you a chapter to read, and it's just a lot of technical details. It's a lot of steps going line by line by line, and you can see why it's true. You have enough to understand this. Later in the semester, I will give you a link to a proof of the fundamental theorem of algebra. My favorite proof uses complex analysis. There is a proof that just uses multivariable calculus. So if you remember your multivariable calculus, you can prove the fundamental theorem of calculus, so the fundamental theorem of algebra, by just using multivariable calculus. Okay, why do we care about this? This now allows us to prove a certain number is transcendental. What we will do is we will show that this number can be approximated by rationals too well. And because it can be approximated by rationals extremely well, it can't be an algebraic number. So it has to be transcendental. All right, so let's try to prove that this is a transcendental number. So we'll do a proof by contradiction. So if not, say it's algebraic of degree d. Can you give me a good rational approximation to this infinite sum? How might you get a good approximation? Take the first term. How about you get a better approximation? First two terms. So let's let Pn over Qn be the sum, m goes from 1 to n, of 1 over 10 to the m factorial. Then alpha minus Pn over Qn would equal the sum m equals n plus 1 to infinity of 1 over 10 to the m factorial. And so we want to see how close are we? Well, the sum m equals n plus 1 to infinity of 1 over 10 to the m factorial. Do you agree that this is less equal to the sum L equals n plus 1 factorial to infinity of 1 over 10 to the L? I'm just putting in all the terms, right? So this is going to be, by the geometric series formula, it's the first term, which is 1 over 10 to the n plus 1 factorial, divided by 1 minus 1/10. What's 1 minus 1/10? So that's going to be 9/10. So I get 10/9. I don't want to write 10/9. So I'm going to just say that this is strictly less than 2 over, I'll just write this, 2 times 1 over 10 to the n plus 1 factorial. Everybody comfortable with that? So I've approximated the error. So now I get alpha minus Pn over Qn is less than 2 times 1 over 10 to the n factorial to the n plus 1. And I'm just writing n plus 1 factorial as n plus 1 times n factorial. But what do we know about the denominator Qn? You know, Qn is my denominator for this rational number. Qn is at most, 10 to the n factorial. So this is basically like comparing this to 1 over Qn to the n plus first power. So we know Qn is at most 10 to the n factorial. Sorry, 10 to the n factorial. Right? The problem is maybe there's some cancellation. I can't imagine that there would be. But that when we somehow add these, we know that the greatest common denominator is at most 1 over 10 to the n factorial. So this means if we divide, 1 over 10 to the n factorial is less than or equal to 1 over Qn. So over here now, this is going to be less than or equal to 2 times 1 over Q sub n to the n plus first power. And so if it's an algebraic number of degree 5, once n equals 6, it's a violation of Liouville. If n equals 12, once n is 13, it's a violation of Liouville. Is this clear? Yes? Or no? Okay, it's clear. Okay, so violates Liouville once n is greater than d, so alpha is transcendental. So we have now constructed a transcendental number. Unfortunately, there are uncountably many transcendental numbers. This is just one. Can you give me another transcendental number? Good. Give me another one.
Any other number?
Good. So you've now given me countably many transcendental numbers. I will show you, I came up with this exercise when I was writing a book a couple of years ago, uncountably many transcendental numbers. So let's consider the binary expansion of any x in 0, 1. So I can write it as, bnx over 2 to the n. So bn is the nth digit in its binary expansion. So all these digits are going to be 0 or 1. If I give you an irrational number, no two irrational numbers can have the same binary expansion. Unfortunately, if I give you 0.011111, that's the same as 0.1 in binary. So it is possible for some numbers to have the same binary expansion, but let's just take irrational numbers. And I'm going to define a function on the irrational numbers as follows. Take the nth binary digit and add 1. So we had 10 to the negative n factorial. This is now 10 to the negative either n factorial or 2n factorial, depending on what the digit is. And by a very similar argument, you can show that this is going to be transcendental. So we now have a function that is always transcendental at irrational inputs. You have to figure out what's going on. You can ask, various questions if you want to about this function. But here's at least uncountably many numbers that we can prove are transcendental. Now, these numbers have tremendous deserts of zeros before their next term. So we're not really seeing all of the interval. Cantor showed us that almost every number is transcendental. We're focusing on very small parts, but at least we're seeing a constructive way of getting a lot of them. So what I wanted to do is just quickly summarize what we did today, because we actually covered a lot today. We started off by talking about finding a good metric. It's trivial to find rational approximations to irrational numbers. Just take the decimal expansion and truncate. The problem is finding a good approximation. And so by using a very large denominator, I can get a good approximation, but I really can't be that proud of doing this because my denominator is huge. So if we're using like 22 sevens, that's pretty good. I'm using 7 as a denominator. We're getting a pretty good approximation. Infinitely often, we can approximate any irrational by a rational p over q and be off by at most 1 over q. Well, this isn't that impressive. It's just step, 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 step. Taking steps of a fixed size 1 over q, I can't hop over by more than 1 over q. So that wasn't a big deal. We then talked about Dirichlet's pigeonhole principle. And so this is an incredibly powerful result. It takes a while to truly understand how to use this well. There are some problems where it's really obvious what the boxes and pigeons should be. There are other problems where it is not clear. It's very similar to proofs by induction. If you're trying to prove the sum of n squared and cubed into the fourth, if I tell you what the formula is, the induction it just writes itself. It's very straightforward. For other inductive problems, it's a little bit harder to figure out what I should be doing. And we saw an example where we gave some integers a1 through an, and it was a little bit of work to figure out what should the boxes be, what should the pigeons be. And the boxes were the non-zero remainders mod n, and there were 2 to the n less 1 possible subsets. That's a lot of possible subsets. We found a really nice family of subsets to look at, where by knowing that 2 of them were in the same box, things were nice. Sometimes when you do problems like this, you say, without loss of generality, let's assume the a's are in a non-decreasing order. We didn't need to do anything like that for this problem, but it's not bad to be aware that sometimes things like that are worth doing. We then proved this beautiful result, and I think this is due to Dirichlet. I'm pretty sure that this was Dirichlet, that infinitely often we can get within 1 over q squared. That's now somewhat impressive. If I want to have 4 digits of accuracy, I only need to use denominators of size 2 digits. If I want to do 8 digits of accuracy, I can do denominators of size 4 digits. So this was a non-trivial result. And then the question was, well, maybe if we just thought harder, we could do better than 1 over q squared. And the answer is no. And the best we can do is 1 over q squared root 5 in general. You can't do better than this for all numbers because of the golden mean. And then you can start asking how many numbers can be approximated this well or better. And there's some beautiful results about this. We talked very briefly about that. And then we went to Liouville's theorem. So I think I jumped over Watt's theorem. We had Watt's theorem, which got a Field's medal, that you cannot do better than 1 over q to the 2 plus epsilon for a algebraic number infinitely often. You can do 1 over q squared infinitely often, but you can't do 1 over q squared plus epsilon infinitely often if the number is algebraic. And this would allow us to prove that they are transcendental numbers. One way to do that is to look at what is the size of all numbers where maybe we can do good approximations like this. And then you'll see that not all numbers are in that interval. So there have to be numbers left over that can't be approximated this well. That's a little bit more work, but we can do it. We then tried to look at algebraic numbers of degree 1. Those are the easiest ones to look at because they're just rational numbers. And we saw that, we can't approximate rationals infinitely well by, arbitrarily well by rationals infinitely often. Well, that's not a big deal because we don't need to try to approximate a rational well by a rational because it's already rational. We then talked a little bit about what does it mean to have repeated roots. And we talked about the formal derivative. You can define anything you want in mathematics. The question is, when is it useful? Calculus, hopefully you've seen applications as to why calculus is useful, why we might want to study that, why you've taken 3 classes. The proof of the fundamental theorem of algebra using multivariable calculus is a nice example of why we care about stuff like this. Every polynomial of degree n with complex coefficients has n complex roots. It turns out by using the formal derivative, we have a really simple way to tell if there's a repeated root. We then talked about the intermediate value theorem and the mean value theorem. These are 2 fairly straightforward results from calculus. They have lots of nice applications. And then we used this to prove Liouville's theorem. If you have a real algebraic number of degree d, then you can't approximate it better than 1 over q to the d infinitely often up to some constant. I might be able to do 1 over 1,000 times 1 over q to the d. That's fine. I'm not going to celebrate that. I care about the q dependence, not the constant outside. And the way we did this is we looked at f of alpha minus f of p over q. F of alpha was 0. F of p over q is a rational number. The denominator, okay, we can write it as an integer over q to the d. Since the integer is not 0, it has to be at least 1 in absolute value. And again, this is a really common technique of I've got something that's not 0, its absolute value, if it's an integer, is at least 1. So then we had 1 over q to the d was less than or equal to the absolute value of f of alpha minus f of p over q. Oh, okay, mean value theorem. So a tremendous amount of mathematics is pattern recognition. When you see something, trying to figure out what should I use? What's a good way to attack this? I want to somehow get an alpha minus p over q. I want to try to estimate how close is alpha to p over q. I've got an f of alpha minus f of p over q. Oh, the mean value theorem relates those two. It relates it with some f prime of c. And I know f prime of c can't be too large. Imagine f prime of c was growing with q. Then when I divide by it, I'm getting something that's getting smaller and smaller and smaller. And so maybe, imagine c2 was like, q to the d. Well, then now maybe I could do 1 over q to the d plus 1 infinitely often. So we just have to show that there is some universal constant. So really, the part about this that we care about is this is the inequality we care about. We don't really care about the one where it's strictly greater than 0. I know it can't be 0 because the left-hand side is non-zero. I care that it can't be getting too large because if it gets really large, then alpha minus p over q could get very small. And what's going on is, I have some interval, here's alpha, and I can just say, look, I'm in some subinterval very close to it. If I look at f prime, I've got some plot for f prime. F prime can't get too large, it can't get too small. And so we then got that we had a contradiction. We got alpha minus p over q was strictly less than alpha minus p over q. And then we used that to get Liouville's theorem to show that this number could be approximated very well by rationals, so well that it violates Liouville's theorem, so it has to be transcendental. All right, so we did a lot today. For the next class, we will then go back and start doing the theorems from chapter 8 slowly and carefully. So this is a good place to stop.